Today we're going to talk about the derivative of a function. This is one of the two big ideas that are calculus. So we've been doing the slope of a curve or the slope of the tangent. Slope of the curve, slope of the tangent are the same thing. If the slope of a curve, y equals f of x, exists at x equals a, that is, the limit as h goes to 0 of f of a plus h minus f of a all over h exists, then this limit is called the derivative of f at a. So now we've added on another term to it. Slope of the tangent line, slope of the curve, derivative at a point. All of those are the same thing. So slope of a curve at x equals a slope of the tangent at x equals a and the derivative of the function at x equals a. Those are all the same. All those things mean the same thing. And what we call it frequently has to do with the context of the problem. What is it that we're trying to do? Now, in addition to finding the slope at a particular point, we can also find an equation for the slope at any point. So the derivative of the function f with respect to the variable x is the function f prime of x, whose value at x is f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h, provided the limit exists. So what we're doing there is we're finding, in general, what is the formula for the slope of any tangent line or the slope of the curve anywhere. Of course, provided this limit exists. We'll talk more about that when we get to the section on differentiability. If f prime of a exists, we say that f is differentiable at x equals a. Now, you may be wondering, why are they calling it differentiable? Well, remember that this is called the difference quotient. So that's where that term comes from. It's from this that's the difference quotient. Otherwise, it would have been differentiable, which makes sense. It's harder to say. Or derivatable. Derivatable sounds like, I don't know, like it's a large helium-filled balloon in World War II. All right, so let's find the derivative of f of x equals x cubed. So f prime of x, which is the derivative at any point, the slope of the tangent line at any point, will be the limit as h goes to 0 of, we're going to have f of x plus h, so that'll be x plus h quantity cubed, minus f of x, which is just x cubed, all over h. There's never a point in going ahead and trying to calculate this, by substituting in 0. It's always going to be 0 over 0. So it never works out that you can just immediately do it. So we're always going to have to algebraically manipulate this in some way. So I'll start by expanding the x plus h quantity cubed. That's x cubed plus 3x squared h plus 3xh squared plus h cubed. And then we have that minus x cubed at the end, all over h. We can subtract the positive x cubed and the negative x cubed, and I'm going to go ahead and also factor out the h in the numerator that's left. So that's going to be the limit as h goes to 0 of h times 3x squared plus 3xh plus h squared all over h. Dividing the h's out, we have the limit as h goes to 0 of 3x squared plus 3xh plus h squared. As h goes to 0, the first term is unaffected, but the second two terms both go to 0. So we get 3x squared. We will learn some shortcuts for being able to take derivatives like that, especially for polynomial functions. It's called the power rule. I know, George, you've already done this in AP Stat, in AP Physics, right? You will still be required, even after we learn the shortcut, to be able to show me that you can do it the long way. Okay, now there's an alternative definition that's occasionally useful. It says the derivative of the function f at the point x equals a is the limit given by f prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. So again, you have a stationary point, a f of a, and you're saying that as x gets closer and closer to a, I'm going to take the difference quotient, which is the slope of the secant line, and as they get really close together, I get the slope of the tangent line. I'm going to change this problem. Let's use change that at the end to f prime at 4. For f of x is equal to x, square root of x, use the alternate definition to find f prime at 4. So that's going to be the limit as h goes to 0 of sorry, forgot. We're using the alternate definition. So the limit as x goes to 4 of f of x, which is just the square root of x, minus f at a, so that's the square root of 4, over x minus a. So this is our alternate definition. So I can make this slightly better, but I'm still going to have to manipulate this by rewriting as the limit as x equals 4. I'm sorry, this should be I don't know why I keep writing a, x minus 4. So this will be the square root of x minus 2 over x minus 4. And if you'll recall from our units on finding limits, what we can do on ones like this where it has that square root plus or minus something, we'll multiply by the conjugate. That is the square root of x plus 2 over the square root of x plus 2. So it's going to be the limit as x goes to 4 of, when I multiply these out, the square root of x times the square root of x is just x. My middle terms will drop out. I'll have a negative 2 square root of x and a positive 2 square root of x. And I'll have a minus 4 all over x minus 4 times the square root of x plus 2. It may be helpful to you, at least to your thinking, to put the x minus 4 in the numerator in parentheses. It's times 1. So since these are factors, both numerator and denominator, I can divide these out and get 1. So then as x goes to 4, I'm going to have 1 over, the square root of 4 is 2, plus 2, it's 1/4. So f prime at 4 is 1/4. We'll also learn shortcuts for things like the square root, the cube root, all those kinds of things. Actually, it's the same as the one for polynomial functions. It's just that you have to rewrite it as a power first. The square root of x being x to what power? X to the 1/2 power. All right, notation for derivatives. Sometimes students complain about the number of different ways we can write the derivative, but you have to understand historically what happened is that calculus was, at least as I understand it, invented, if you want, discovered, depends on what your point of view is, by two different men, basically at the same time, in two entirely different countries, with no correspondence between them. In England, it was done by Isaac Newton. Famous for all kinds of things, gravitational laws, all kinds of stuff like that. In Germany, it was done by a man named Leibniz. Again, almost simultaneously. And they had different ideas about how to approach it, but they ended up in the same spot. But they used different ways of writing it. And each of them has, something to say for it. We've kept both kind of as a homage to, to both of them. But for the function y equals f of x, each of the following denote the derivative, f prime of x or y prime. These are both Newton. You don't need to know that, but these are both Newton. He did all the stuff with primes. All these other one are Leibniz. dy dx, df dx, or d over dx f of x. I particularly like dy dx because it reminds me that this is a slope. It's a change in y over a change in x. What Leibniz thought of is he thought of this in terms of infinitesimals, is what he called them. At least that's how it translates into English. What he did is, instead of the difference in y over the difference in x, is he said a really small difference in y over the corresponding really small change in x, which is what we're doing. You don't see this one very often, df dx. You will see this. I kind of like this one also because it becomes an operator. This tells you take the derivative with respect to the variable x of the thing that comes after it. On the other hand, the Newton notations are nice because they're shorter. All right, so we can, in addition to being able to take an equation and use the limiting process to find the derivative at a point or the derivative function, we can also estimate derivatives. We're going to do it two different ways. First, we're going to estimate derivatives graphically. So for these, what we have to remember is that graphically, the derivative is the slope of the tangent line. So, for example, here at x is equal to 4, if I was to draw a line tangent to that, what would its slope be? 0. Yeah, slope would be 0. So on the graph of f prime, I'm going to put a 0 at 4. Now, all these other ones, this one, it's a little past, but what they've done is they've given us the derivative, a point at 0, a point at 1, a point at 2, and a point at 3, and the point at 4. What we're going to do is we're going to estimate the slope of the tangent line at each of those points, and then we're going to stitch all that together to see what the graph of f prime looks like. So starting right here, what you can do, if you have a straight edge handy, or if you want to grab one of the rulers off the back, or you can pull out your student ID or whatever, the easiest way to do this is to actually take something straight and put it right up against this so that it looks tangent to the curve at that point. I'm going to try to do it. It's really, really difficult, but it's going to look about like that. That's not very good. Start a little further over. And just lightly sketch that. That's still not great. Ooh, that one's good. And what I usually do is I go ahead and draw it one to the right or one to the left, so that if I think about a slope triangle, the horizontal distance is 1. And then here I just need to estimate, well, what is the vertical distance? It's about, I don't know. What do you guys think? It's bigger than 2. And it is not an exact science by any stretch of the imagination. So 2.2? Okay, great. So at 0, our slope is about 2.2. At 1, I'm going to try this again. Nope. That's not bad, but it's not great either. It's a little shallow. Ooh, that one's pretty good. So again, kind of a slope triangle thing. If I go over and up, let's see. That's at about 2.5, and that's at 4. So I would say the slope is about 1.5. And again, don't make yourself crazy when you're doing these. Now, here at this point, it's near 0, but it looks to me like it's going down just a little bit. Not a ton, but maybe about like that. So again, if I'm doing a slope triangle, it doesn't go down very much. What, like maybe 0.3? So the slope there would be negative 0.3. So somewhere about there. And then I just keep going. So that one's about like that. That's at about 3, and this is about 0.5. We'll call it negative 2.5. We're almost ready to connect those, to do the derivative. The only one thing I want to point out is, like in this area between this high point and this low point, is this point where the line is going to be steepest? So if I went further over here, the line's less steep, right? If I move a little further over here, look somewhere right about in here, the slope is steepest. And so that's going to be, because the slope is negative, that's going to be where the slope is most negative. So at about 3.5, it's going to be at its most negative. So I'm going to put another point a little further down. And then over here, it looks like it's steepest, I don't know, somewhere. Looks like it's a little steeper there, but it's pretty close, so I'm not going to bother with it too much. I'm going to, go slightly up. And then something like that. So the question that students always ask, where, if this was on a quiz or on a test, what would you be looking for? I would be looking for, where is the slope 0? Do you have those? Where's the derivative 0? It should be at about 4 and a little before 2. And is the derivative positive where this slope is positive, and is the slope negative where the slope is negative? Right? The derivative is negative where the slope of the original function is negative. We're not going to major in this at all. It used to be a big deal where people would use derivatives to help you graph things, but not nearly as much anymore. All right, last thing, estimating derivatives numerically. So, use the following table of values to estimate f prime at 3.2. Well, f prime at 3.2 is the slope of the tangent line, which is the instantaneous rate of change of f at 3.2. Unfortunately, we don't have any information about what happens at 3.2. However, what we can do is this. we can say that f prime at 3.2 can be approximated by an average rate of change. Of f, and what we want to do is we want to take the smallest interval that contains x's 3.2 that I have. So I'm going to use this interval. So I'm going to say on the closed interval from 3 to 4. That's equal to 30 minus 26 over 4 minus 3 is 4. Do I have any confidence that this is exactly 4? No. Do I have any real confidence that it's close to 4? No. But this is the best I can do. If they asked, for example, what's f prime of 3, I would do the interval from 2 to 4. Go from one side to the other instead of just on one side. All right, any questions about that? Okay.